me personally, I think is going to be the wave of the future of farming in the 21st century. And let's go and continue here. By the end of the webinar, I hope participants will be able to list and describe how physical and chemical biological disturbance impacts soil function, how soil biology impacts soil function. We're going to go over some case studies throughout the country that I've collected, farmers that farm in nature's image and utilize manure accordingly. And number 4, what are the common management principles these farmers apply when utilizing manure? First, I want to make sure that we're all on the same page. Soil health and quality is the capacity of a specific kind of soil to function within natural and managed ecosystem boundaries to sustain plant and animal productivity, maintain or enhance water and air quality, and support human health and habitation. There are 5 broad ecological functions. I'm not going to read them. This comes from the nature and properties of soils, as you can read them yourself. I'm going to be explaining that next slide. Remember, Kristen was talking about there's going to be a little video clip. What we're going to show here is 2 demonstrations. That one is this lake demonstration, and the other is the little miniature rain simulator. When I go across the country, and whether I talk before an audience, no matter if it's farmers, extension, or NRCS, or district employees, I always start off with this demonstration. And one of the things I like about this lake test is very visual. And the way this lake test works is you have 2 jars of water and screen. You collect 2 aggregates. You're going to see 2 aggregates here. Leslie's going to show this. There's 2 aggregates. We recorded this. This is our livestock specialist here, a grading specialist. He's dropping the 2 aggregates. On the right-hand side is conventional till. These are 2 soils, the same soil type. They're only a mile apart. And the left side is no-till. On the right side is conventional. You can see the slaking is immense on the conventional. The biotic glues, the cementing agents, are no longer present in that soil. On the left side is the no-till. It has been no-till for 40 years. The organic matter is 2.75%. The wooded lot from that farm is 3%. The soil on the right side is less than 0.5%. So when you start tillage, you stimulate these coprotrophic bacteria, this bacteria that like rich carbon substrates, and these glues are carbon-based substrates. So Leslie's going to show the other little clip. It's going to be the miniature rain simulator. Like I said, I use those 2. So when we talk about the soil ecosystem, I tell them how tillage disturbs it. Now these are the same soils again. Now Kevin has on the point of the blue food coloring is a no-till, that's in the same no-till soil, and Steve with the yellow coloring is pouring the conventional. We want to see in this little miniature rain simulator the macro porosity and the micro porosity, the glues, the pores held intact, and you notice the infiltration on the no-till soil, how quickly the water infiltrates. We always start off with this demonstration because most farmers, even myself included about 7 years ago, I used to think if I tilled the soil, I actually incorporate more air into the system and actually increase the soil tilt. These 2 demonstrations show the opposite. You can notice on the left how the water ponded off where Steve is holding it. What happened to that? What's going to happen to the water in that system? The water's going to run off with the fertilizer and the pesticides and go down the river. The soil on the right, with a higher organic matter, higher CSC, is going to infiltrate. Soils want to do 2 things. It wants to capture water and able to filtrate. So let's go to the next one. Thank you, Leslie. It worked great. That's how I start off my demonstrations, because I have learned, unless I show these demonstrations, our farmers have a lot of paradigms about our way our soils function. I had certain paradigms, and the best way to do is to shatter paradigms and start at base 0, and then from there we can start talking about soil as a complex ecosystem. For some reason, mine doesn't show the PowerPoint. Okay. Okay. Leslie, we are not seeing the PowerPoint on my side. Okay, I guess we'll go to the computer. As you see these soils on the left-hand side, on the side, you'll see the forest soils. These soils are the same soils, ladies and gentlemen. Can you believe that? It's the same soil. I want you to notice the forest soil, how dark and how you can see the humidification on that soil. And you can see that the darker colors. The right soil is a 17-year soybean, conventional tilled. The soil on the right is, oops, I lost connection. Leslie?
Excuse us, we're having technical difficulties.
We have technical difficulties here. Leslie?
If you want, just tell me when to move your slides and I'll move them ahead. I can
Okay,
see them.
move them ahead. We're not getting it. It looks like we've lost some connection here. I can't even see the PowerPoint.
We can see it just fine. Just go ahead with your presentation and tell me when to advance your slides.
Okay, but I can't see them.
You don't have your slides in front of you?
Nope.
At all? Okay.
Nope.
I'm gonna have you reopen the. Try hitting F5.
Okay. Nothing.
Try logging back into the room.
Okay.
And we managed to lose it on 2 computers at once.
Ah, beautiful. Okay, I think we're still waiting for.
Okay. Leslie, could you go ahead to the next slide?
Oh, back up, back up. Back up again. Back up one more time. Okay. For some reason, okay. You'll have to move them for me, okay, Leslie?
I can do that. Just tell me when.
Okay. We've had some technical difficulties, but we are going forward here. And I have 2 pictures of side by side of 2 soils. On the right hand, you see a conventional soil. This soil, as you can see, is of a different color. It's got low porosity. It's a bacteria-driven system. It's not efficient for managing carbon. It on the soil on the left is the higher CSC, higher percent organic matter. It has larger porosity. This system has a wide array of soil organisms. And it's got fungal, bacteria, and the other organisms, and the one on the right is bacteria-driven. The system on the right has compaction organisms predominantly, and those are bacteria. So the soil on the right is not going to be as efficient for cycling nutrients, and the soil on the left is going to be more efficient for cycling nutrients. It's real important to understand our context when we're dealing in the watershed, and we understand that not all soils are functioning at the same level, and we cannot treat them the same. So it's really important that we understand this concept. Let's go to the next one, Leslie, please. Also, because we have many people in the West, I grew up in the West, we had those short street prairie soils. They also, at one time, were functioning at a high level. And what you see on the right is, you can imagine, we have a lot of till systems. In fact, a majority of our research has been based in the last 50, 60, 70 years or more, has been based on till systems versus no-till systems. Let's go to the next one, please. This particular is an electron microscope image. You can see on the upper 9 millimeters the soil depth, and notice the giant pores. Those pores are held together by these glues like glomalin, created by fungus. Earthworms create these glues. These bacteria create these glues, also root exudates. All these biotic glues, these cementing agents, help keep our soils porous, keeps the pores open. That's why you saw in that little miniature rain simulator how the water was able to filtrate. On the right-hand side, you see tilled soils with the upper 9 millimeters. This soil, you see very little pores. You get a crusting effect. That's why I tell, when I talk to our landowners and to groups, we don't have a runoff problem. We have an infiltration problem in this country. We have a hard time getting the water into the soil. Runoff is a symptom of poor infiltration. Okay, good. Let's see if I can get to the next slide. I think I have control now. Okay, this is a picture of a model of a little microaggregate. I want you to notice, here you got the fungal hyphae, particular organic matter. Here's the microstructure of the clay, microaggregates of silt and clay, the plant and fungus debris. These little ones here are the little microaggregate, and this is the macroaggregate. Now, look what happens when you do mechanical tillage like disking or any surface disturbance where you disturb the agrosphere. What happens here is when you open that soil up, you shear the aggregates, smash them, and you expose them to oxygen. Then these coprotrophic bacteria, coming from the word copious, meaning they love rich carbon substrates, allotrophic bacteria like the more recalcitrant carbon substrates. But again, when you disc and you create soil disturbance, you get these microbes to start eating those cementing agents that hold this habitat in place. When those particles, when the cementing agents are gone, the particles collapse, the particles fill in the pore spaces collapse. One of the things that as I go across the country, and I myself had this after 7 or 8 years of school in soils, I actually walked away thinking that, you know, the soil, there are many things in interaction with the soil. I call it the black box syndrome. I actually thought that, you know, here, well, plants are absorb nutrients from the soil solution, soils exchange cations with soil solution, minerals release nutrients from the soil solution, and then you have roots giving off, you know, exchange CO2 and oxygen with the soil solution, and then you have fertilizer doing that, and Les is going to show the next video. But here's the thing, ladies and gentlemen, what I really saw was a very mechanistic way of looking at the soil system. I thought of it as a just giant mass flow interception diffusion box where all these things are happening. And Les is going to show us the next video. But in reality, it's much more complex and beautiful than that. I have realized in the last 6 or 7 years that the soil system is this very complex, very beautiful system, soil ecosystem, and these organisms interfacing. It's these organisms that help maintain our structure. They're the organisms that help feed the plants, and the plants feed them. You can see this beautiful video by Dr. Chris Nichols. Here you see these nematodes. when the bacteria start populating, the nematodes are like lions in the Serengeti. They'll feed on this bacteria, and they can release anywhere from about 16 to 118 pounds of N just by that predation. You have cilia, you have all these organisms in this fantastic ecosystem. The more we understand about this soil system, protect it as a habitat and treat it that way, the more we can become sustainable and manage more manure accordingly. Let's go to the next one, please, Leslie. Thank you. So now I don't have that mechanistic view of the soil system, but I view it as this beautiful, complex, like again, system. And our landowners, when they see that video, they really appreciate that. Here we go. Just past that. So what is the result of this view of the soil, this misconception of the soil? On the left, I take these, as I fly across the country, I take these pictures, and I want you to notice this urban disturbance. I have a brand new house. They have compacted my soils. They move all the topsoil, they compact it, and then they put two ugly shrubs, and they call it good. Then I have to spend $3,000 to remove our soils. Our soils were just treated like a groin, like a medium for structures. Look at the agriculture disturbance, as you can see. And what are the results of that? This was a study that was done in 2006. I want you to notice the bulk density of soils in New Jersey. This was done by Chris Smith, retired soil scientist, and David Freeman. Bulk density, for some of you who are not soil scientists, bulk density is the measurement of the pore spaces. It also measures the particle space, but I don't care about the particle. But I'm really interested in the pore space. Concrete is 2.4 grams per centimeter cubed. I want you to notice that in the soil here, on the wood lot, the bulk density is 1.42. You notice here the permeability is 15 inches per hour. But I want you to notice here, as we go to the subdivision one, 2.03. And I want you to notice here the permeability of 0.3. The reason I want to show this is because a lot of times agriculture is looked at as the major source of non-pollution. But can you imagine there's a lot of people out there, urbanites, applying Miracle-Gro to green concrete. As you can see, the bulk density of that is horrific. And look at the football fields, 1.95. There was an article many years ago, they call it the killing fields, titled the killing fields because kids were getting killed in the football field, not by the contact, but by landing on the soil. Here, we have a picture of a miniature rain simulator. This was taken by J.B. Daniels, grazing specialist in Virginia. I want you to notice that on the bottom here, you have these little containers capturing the water from these pans of sod collected. As you see, you have the continuous, you have the good rotational, you have the external rotational. I want you to notice how much water runoff is coming from the continuous, and yes, there's a cover. I want you to notice the good rotational, how very little ran off, and look how much infiltrated. Same thing for the external rotational. Look how much went into the soil profile, and look how much ran off. This is an amazing tool. We just bought one here at the Tech Center. I definitely recommend. I think this would be one of the best ways of teaching conservation. First thing I ask the audience is, on this overstocked, overgrazed pasture, I ask our participants, and when I go speak, says, why did we have so much runoff in this overgrazed system? And then the majority of the audience says, well, we have poor roots, we have compaction, and those may all be true, but in my humble opinion, I think it's because our canopy is so small that the height of the canopy is not high enough. We need a higher canopy to disperse the kinetic energy of that raindrop. That raindrop comes at 20 miles an hour, an incredible velocity, and I personally think because our grazing systems are overgrazed, we have a majority of our water running off the land. So this is the results. We till our soils and we destroy the aggregate stability on the soils. We pour concrete, we have asphalt, we have rooftops, we have green concrete. And here you see the results of that. We overgraze our systems, and we have the result of a lake that's right next to my house. As I fly in, I took this picture by myself. I always, when I fly across the country, I take a window seat, and what I can see here, that's not the normal color of this lake, but I want you to notice the beautiful diaper around that. I called buffers diaper practices. I like diapers. They're important, but I wanted to notice how wooded, shrub, grass, how large it is, and yet our lakes still look like this. Personally, I think we have, throughout the country, diminished the soil function. Is it possible that we've created our own droughts by diminishing the soil function? We'll talk about that, continue on our journey here. And I think a majority of the reason for this is because as I walked away from college, 8 years of school, for some reason I think maybe I ate the books or whatever, and I thought maybe I should have had more of an ecology-based background, because what I love about ecology, it focuses on the interconnectedness. Who would have known that these microorganisms are so deeply connected with the cow, with us as a human being? In fact, all of us today had contact with these organisms in a way, because they're the ones that provide